this is Schrodinger's Pokémon, Observability for Chaotic Load Testing. This is my attempt to put together 3 things I'm a fan of: the Pokémon franchise, K6 the load testing tool, and New Relic. But first, let me tell you a little bit more about myself. I'm Nicole van der Hoeven. I'm a developer advocate at K6, which basically means that I try out cool things and tell people what I've learned. I've been in testing, and particularly load testing, for the last decade. In recent years, I've moved towards open source load testing tools in particular because I enjoy the speed of innovation, the community, and the flexibility that they come with. I'm also Team Mystic on Pokemon Go when I'm not being Team Rocket, and my shield starter was Grookey. Schrödinger's cat is a thought experiment created by physicist Erwin Schrödinger. I'm sure he intended for it to illustrate a point about quantum mechanics, but I'm going to liberally repurpose it for something that makes sense to me: software reliability. Now let's say we have an application. That's our Pokemon. When we deploy our application, we put it in a box, an environment that is bounded by physical and virtual resources. Now imagine this application, once deployed, has to withstand some stimuli in the form of high load and the chaos of real users accessing the application. How does the Pokemon handle it? The problem is that due to the complexity of modern application architecture, the box that the Pokemon is in is initially pretty opaque. We can't see into it, so we don't know how it's doing. Is the Pokemon even alive, or is it dead? My goal in this presentation is to figure out a way to see into this box. Here's the plan. I want to deploy an application, our Pokemon, on Kubernetes in the cloud. I'm going to run load tests and some chaos experiments against it. But before that, I'm going to set up monitoring on the application components so that I see what's happening every step of the way. So here's the problem. I'm a tester, not a DevOps engineer. I've definitely done load tests, but I've never set up a Kubernetes cluster, and I've never run a chaos experiment. So this exercise is also a test to see how easy it is to get going with chaos engineering for a beginner like me. The first step was building the application. It is a RESTful API that lets you query a database to fetch information about a Pokemon, an ability or move, or even an item featured in any of the Pokemon games. It already came with a Docker Compose file, so all I had to do was create YAML files from that. I created a managed Kubernetes cluster consisting of 2 nodes on DigitalOcean, and I applied the manifest files to my cluster. The application has 4 main components or pods: the web component, the app itself, a database, and a cache. I created a replica of the web and app pods and set up anti-affinity rules so that the replicas would not be deployed on the same node. By the end of this, I had a working application. Yay! I'm breezing over this for the sake of brevity, but actually just getting to the point where I had a working application took hours of Googling, reading tutorials, and asking people for help. Again, Kubernetes noob here. Now for the chaos. Chaos engineering has the same goal as performance testing at its heart, which is to improve application reliability. However, it differs in its approach. Traditional testing is usually about preventing issues. We identify performance bottlenecks so that we can fix them before an application goes live. We want to prevent issues from occurring in production. Chaos engineering takes issues and failures as a given, so it assumes that failures are going to occur and attempts to improve the way that the application responds to the failures instead. The first step in chaos engineering is to define the steady state. The steady state is the control state of a system and can be defined with metrics such as error rate, response time, or resource utilization. The purpose of having a steady state is to validate the stability of the application before any chaos experiments are run. This is where New Relic comes in. Luckily, setting up New Relic to monitor my application was pretty easy. I used this handy tool to generate a manifest file that I copied and then applied to my cluster. It started up a lot more pods that collectively sent information to New Relic about the application. I set up dashboards to make sure that I could see things like the resource utilization, including CPU, memory, and the network of the two nodes. I was also able to get more granular insights about my Kubernetes cluster and see things like whether any pods in my cluster were restarting. In performance testing, the steady state is kind of like what we would call a baseline. It's the control sample, the state, before you introduce artificial load and events to a system. It's a nice clean state that lets you directly attribute later changes in behavior to the intervention that you are attempting. Because I knew that I would want to find out how much load my Poke API could handle, I also ran a baseline load test. To do this, I used K6. K6 is an open source load testing tool written in Go, although K6 scripts are written in JavaScript, making it substantially easier to get started with. This is what the K6 script looks like. The bulk of it is in this function here, getPokemon. What the script does is it queries the Poke API for a particular Pokemon using a list of Pokemon that I've saved in the CSV file. That way, it's not requesting the details for the same Pokemon for every request. Then the script does a variable think time. I put this function in as a scenario to be executed so that I can control the test parameters for it separately when we add more scenarios to it later. I also defined thresholds, such as that the number of failed requests should be less than 5% in total. K6 happens to integrate with New Relic as well, so I made some modifications to the script so that the K6 results would be sent to both K6 Cloud and New Relic. I ran the test with 60 virtual users for over an hour, and I monitored both K6 and New Relic to see whether the application could handle it. Having the metrics piped out to New Relic via StatsD was useful because it meant I could view those results within New Relic as well. This gave me an idea of how the application behaves without the manufactured chaos, both with and without load. The second step is formulating hypotheses. A hypothesis is a statement about the test that you are attempting and how you think the application will respond. In testing, this is like setting pass or fail criteria. When starting with chaos engineering, it's a good idea to keep your blast radius small. That is chaos speak for starting with small, contained tests that build on each other. That way, you're slowly introducing variables and you can easily spot where and why things start to go wrong. I defined service degradation as an error rate and response time that was at least 5% greater than that of the baseline. And then I formulated hypotheses about the 3 experiments that should not cause service degradation. Firstly, load of 100 virtual users. Secondly, terminating an app pod. And thirdly, terminating a web pod. The third step is actually carrying out the experiments, and the fourth one is analyzing the results, and I'm just putting them together because it's a good idea to look at the results and understand what happened after each experiment before you move on to the next one. So they're actually kind of interconnected. So let me show you what happened. This is K6 Cloud, and we're looking at my baseline run of 60 virtual users, which I ran for 60 minutes and 30 seconds. It ramps up gradually in the beginning, holds steady for about an hour, and then it ramps down. Since this is our baseline, I'm going to set it as the baseline so that we can compare things more easily to it later. We can see that the average response time is 10 seconds, which typically isn't a great response time, but I already know that this is just a demo application, so I'm just going to go with it. And if you look at the HTTP requests here, we do see a few errors even at the baseline level. Now this was a little bit to be expected because I do have a CSV file of Pokemons that the script is going to query our database for, but not all of the Pokemons that are in there have been put into the database. Some of the newer or less popular Pokemons aren't in there, so we do expect some level of errors. Instead of getting this error rate to 0%, I'm just going to look at how many errors there were and use that as a starting point for comparison for future tests. This is the New Relic data for the same baseline test, and I can see that the CPU and memory and network are looking to be expected. Nothing is really jumping out at me. I can also go into here to look at my cluster. It doesn't look like there were any pods that were terminated during it. And I can also look into this K6 tab to see everything that K6 is sending directly to New Relic. So I think this is a good place to start, and it will be acceptable as our steady state. In reality, if I saw that at this stage we already had an average response time of 10 seconds, I would probably suggest that we go and look into the code a bit more to see why that's happening. But for the purposes of this demo, I'm just going to take that as the steady state and then go forward from here. So let's go back to K6 Cloud to compare our baseline test with our experiment to see how well the application responded. I'm going to select the 100 virtual user test here, and we can see that this is comparing those two tests with the number in green referring to the baseline test and the numbers in blue referring to the experiment. Right off the bat, we can see that there was a threshold. The threshold that we set for the error rate passed in the baseline but did not pass in the experiment. We'll look at that later. We can also see that there was a slight decrease in throughput in the requests per second and a significant increase in the response time. So this is the baseline test at the top and the experiment at the bottom. The experiment shows error rates that pretty consistently went above 5%. We can confirm these results in New Relic as well. Even though the CPU and memory utilization of the node seemed relatively stable throughout the test, if we look at the K6 results here, we'll also see that the number of non-HTTP 200 responses was increased from the previous test. So this experiment shows that the application isn't really well equipped to handle the load of 100 virtual users without experiencing significant performance degradation, according to our guidelines. So let's dial that back down to 60 users, which is the baseline that we already had, and let's see how it responds to terminating one of the app pods. This is back to the baseline on K6 Cloud here, and I'm going to show you the result for the termination of the app pod. This script is very similar to the baseline script, except that I added an additional user. There is a K6 extension called XK6 Chaos, which was created by my colleague at K6, Simon Aronson, and all I had to do was create a new K6 binary using XK6 Chaos so that I could run chaos experiments. After that, it was a matter of importing the XK6 library and then adding a scenario to the K6 script that would terminate the application pod about 30 minutes into the test. Looking at the test here with the baseline test on the left in green and the app termination experiment in blue on the right, it seems to have fared significantly better than the load test. The average response time was only slightly higher. The threshold that we set for the error rate still passed. If we look at the charts here, we can even identify the point at which the app pod was terminated, about 30 minutes after the steady state began. There is a slight increase in the error rate here, but it looks like the cluster worked as expected, created a new pod, and the application continued as normal. The error rate is very comparable. Again, we see that large spike in the middle of the test, but then it goes back down to reasonable levels. New Relic also shows that little bump here in the CPU utilization and a slight one in the memory as the cluster struggled to replace the pod that had been terminated. Looking at the cluster tab here, there's the little spike of the one pod that suddenly stopped running, and it was an app one. So the test functioned as expected, but the application as a whole recovered from it pretty well. Now let's see if the same behavior holds true for when I terminate a web pod. Okay, back to K6 Cloud. Let's select this test to compare with. Again, baseline on the left, experimental web termination on the right, And we see that the response time was slightly higher again, which tracks with what we saw from the termination of the app pod, but the threshold that we set did not pass in the experiment. Looking at the charts here, we see that familiar bump about halfway into the test when the web pod was terminated. And let's look at the threshold. Right, that's the baseline at the top and the experiment at the bottom, and there is a marked increase in the error rate after the web pod termination. New Relic also shows a sharp increase in non-HTTP 200 responses just after the restart happened. So let's recap the 3 experiments. The first one was to simulate a load of 100 virtual users hitting the application. That test failed because both the error rate and the response time were significantly higher than that of the baseline. The second experiment involved terminating the app pod about 30 minutes into steady state while there were 60 virtual users that were being simulated accessing the application. And that test actually passed. Both the error rate and the response time were within acceptable limits, that 5% leeway that I'd allowed, and the application remained healthy throughout the test. The third experiment was pretty similar to the second, except instead of terminating an app pod, I terminated a web pod. And there were significantly different results. While the response times were only slightly higher than that in the baseline test, the error rates were more than 5% higher than in the baseline. So let me step back here and summarize what I've done. I deployed an application on a Kubernetes cluster on the DigitalOcean cloud. I installed New Relic agents on the cluster. I defined the steady state by observing key system indicators both with and without normal load. I defined hypotheses for my experiment, including high load and terminating replicated pods. I carried out the experiments using K6 to generate both the load and the pod termination. And then I used K6 Cloud to check that the experiments themselves had been executed as expected. I analyzed the effects of the experiments on the application using New Relic 1. What I've demonstrated here is only the beginning of chaos engineering. There is a lot more that I can do from this point. I would probably try to fix some of the issues that I identified before launching new experiments, as there's not much of a point in expanding the scope if I already ran into some problems. Some things I could do would be to scale out the cluster by adding nodes and replicas to improve its resilience. I could also add resource limits and health checks to the pods in the deployment files to get more granular insights than just running or terminated, because a pod can be running, technically, and still be in an unhealthy state. As far as other experiments, once the issues are sorted out, I thought about terminating the Redis cache to see if the application can continue to serve requests without it. I could also expand the types of experiments by artificially increasing the CPU or memory. This can be done with a K6 extension called Kubernetes Jobs by my colleague Daniel Gonzalez Lopez. So just to wrap up here, let's go back to our Pokemon in a box. When we're testing an application for its reliability, being able to see into this box is essential. Without it, we can launch test after test against the application, but we don't get any feedback in return. So even when the load testing tool is giving us information about the test itself, it's not enough, because it's only telling us what we're doing and not how the Pokemon is doing in the box. That means we also can't really draw any meaningful insights about how the Pokemon will behave when exposed to the real world. Observability tools like New Relic make the box transparent so that we can see what's actually happening. Setting up the right monitors lets us get acquainted with how the application behaves when it's not under stress, which also lets us identify immediately and perhaps even set notifications for when it's struggling. It gives us a better understanding of the events that our application cannot recover from and those that it can take in its stride. In the end, it's only through observability that we can determine whether the Pokemon is alive or dead. I'm Nicole van der Hoeven, and thanks everyone for listening.